I'm going to look at the example, the spring example from the lecture slides, chapter 14, section 3. Okay. So what we're doing here is we have a block connected to a spring. It has some initial velocity associated with it as it's traveling down a incline. And what we're looking for is the distance, how far it's gone when it stops. Okay, so we're going to have a few components here to think about. We're going to have gravitational work being done. We have an initial force here pulling, or we have a not shouldn't say initial force. We have a constant force pulling down. We have initial velocity associated with it, and we also have a spring, right? So we have a spring that will be stretched as this block moves down. Okay, so we have to include all those components. Okay. Okay, so apply the principle of work and energy, which we expected. Okay, so just going through this, first thing you need to do is, you come up with in this case, they have a diagram, free body diagram and kinetic diagram together. The author just put it as the free body diagram. So first thing you have to define is what you're talking about in terms of position. Now, different ways to look at this. In this case, the author chose to define another distance from our starting point to S2. Um, it might have been easier actually if you just did like a delta S from S1 to S2, then add S1 at the end. Okay, but you'll see how the author does it here. All right, so we have the work and energy equation to use. We have some initial energy defined as T1 uh, in terms of our block, and some work is done on it, going from point or position 1 to position 2, and then it has some final energy associated with it. Okay. So the first part of it, what we can do is we can actually go through and define the works. Okay, the work being done by three different forces. Okay, so first one is due to the force, the work of the force being pulling straight down on it, which is essentially just um, distance. This is the distance times the force. 100 newtons times whatever distance it is. And like I said, you could have defined this as a delta S and just saying delta S is equal to S2 minus S1, but the author did it this way. So here's the distance that it's traveled. So what's the unknown? In this case, S2 is the unknown. So we just have S2 minus zero point 0.6, which was already defined for us here. The second part of this is the work of the block weight. Okay. Here is the weight of the block, which we started with 10 kilograms times 9.81 meters per second squared. And then the distance that it's traveled downward, okay, which is, if you here we have our 30-degree angle of 30 degrees. So if you, one way you could think about it is having another parallel line here. It's going down 30 degrees, and we're actually traveling down a certain distance. And here's the distance. Here's my delta S. And of course, it's that distance, whatever this is, the delta. The delta S is essentially, from here to here, right? The distance from here to here, which is this what's in between the parens here, times the sine of 30 gives you the actual vertical distance that it's traveled. Okay. Well, as before, you just write 10 times 9.81 times the sine of 30 gives us 49.05, and then here is our delta. Okay, or the distance, the actual distance related to S2 minus 0.6 is our delta from here to here, delta S. Okay, the next one is the spring. Okay, so here is our K that's defined, and by definition it's 1/2 of that. And the reason it's negative is because it's going in the opposite direction of our motion. Okay, so the same thing. And here's our delta S, which is essentially, here's our distance that's traveled. And we just square that, we square that term. And here's our form of the equation. Okay. So, it could have been solved where this is just delta S, delta S, delta S squared. And it might have been a little bit easier doing that. Okay. But now we have, here are the work components of this equation, right? Now we also had one other thing, and that was the initial kinetic energy that this block had, which is 1/2 mv squared. Okay, so that needs to be considered in the equation also. Okay, so when we do that, what happens is here's my T1, so here's the initial kinetic energy. The first one here, I'm just going back, here's due to the force, the 100 Newton force. This is the work due to that force. Okay, then here is due to the gravity. Here's gravitational work. And the last component here is the spring. Okay. All right. So just combining the terms, what we're going to have is, this looks like our quadratic formula here. And you can make this delta S. This is like delta S here also. So you'll see that putting it in the standard form, ax squared plus bx plus c equal to 0. Here's like our c coefficient. And then this essentially is our b coefficient, and here's our negative 100 is our a coefficient. So if we go ahead and just substitute in, like I said, I think it's easier to look at it as just a delta S, but okay, you're doing it in this form. So we're saying delta S, or whatever the term is equal to, here's our components when you substitute in for each of the coefficients. And it doesn't make too much of a difference, like maybe it's easier to see it though when you write it out. So when you do that, you solve for it, you have only one root is positive and one is negative. So this comes out to be 2.09, add 0.6 to it, and then you have your total displacement from our original position, which was essentially just, if you go back, we started off with 0.6, and then the whole distance was 2.69. So about 2.09 meters was our delta S, how far it went down further. Okay. Okay.